For the last problem I'm going to do here today, the dark green folder in the current module should have all the handouts that are being used in this demonstration. So we're doing a one sample NHST for the mean. So a null hypothesis statistical test for the mean. And what I want to do is I want to do an Excel demonstration for this. All right, so just to make sure that you know how to actually use this in Excel, then you sort of have a template that you can always refer back to. All right, so again, this, if you bring this up, this should be in your the dark green folder. If you can't locate this, if you want to follow along with that and with it, and you can't locate it, just give me a heads up. So here's what we have. Now the idea, and I'm going to so this little template is something that we can use all the time. So the problem is that you want to assess the accuracy of a company's over-the-counter radon detector. So you got a random sample of detectors, and they were exposed to a calibrated amount of radon, in particular 105 picocuries per liter. So first, we want to test the claim that the detectors are not detecting the correct level of radon. And then second, test the claim that the detectors are under detecting the radon level. And the subtle variations between those is the difference between a one-tailed and a two-tailed test. All right, so the first thing I'm going to start with here is I'm going to go ahead and convert this to a claim. Okay, so let's do the claim. So the claim is that the detectors are not detecting the correct level of radon gas. Okay. In this context, I think we can interpret this as not detecting the correct level of radon gas would be interpreted as a strict inequality. In other words, so the value is 105, and the claim is that it should actually read 105. So I think it's safe to say that in this context, what we have is, or if we're translating this, we're saying that mu does not equal 105. Okay. Again, that is a strict inequality, so that would be the null hypothesis, the alternative hypothesis. Okay, that's the alternative hypothesis, which means the null hypothesis would then be the exact opposite of that. So H sub 0 would be that mu equals 105. Now again, what is mu in this context? So just to clarify, the notation here, and this is always a good habit. So mu is the average detector reading when exposed to 105 picocuries per liter. So that is what mu actually is in this context. The drawing for this is easier in the whiteboard, so I'm going to go back to the whiteboard really quickly. So our drawing here then would look something like this. So we have a distribution of the actual readings and the average of those readings. We're hypothesizing, even though we might not believe it's true, that the average is 105. If we're using an alpha level of 0.02, then there's a value, there's a range down here that would surprise us and a range up here that would surprise us. And these would be half of alpha or 0.01 each. So that gives us a picture of the critical region. So for this one, that is a good question. So if I go back to the, let me go back to the desktop here. So I'm focusing on this question here. So test the claim that the detectors are not detecting the correct level. So this not detecting the correct level, because it's saying not detecting the correct level, that's essentially saying that it doesn't equal 105. So that means anything below 105 or above 105 would be surprising. So that's why we know it's a two-tailed test. Yep. Now, notice that the second part of this essentially is asking the same question, but it's asking it in the term of a one-tailed test. So we'll come back and talk about that in a second. All right. So what we have here then is, so here's just sort of a restatement of the problem, and then we have the data that's been recorded, and I put it here in column B. The key is there is nothing else in column B. That's very important for the template that I've given you here. So I can get the mean, standard deviation, and sample size using these functions. Okay. So again, the main point here is that this is the, so what we have here, this is the sample data. Okay. This, what we have here, this is the sample data. Or in this case, our sample data slash our sample statistics. Okay, so that's what we have here. Now, this is the null hypothesis. I'm going to see if I can cheat and borrow this. Yeah, I think I can do that. So this is just our null hypothesis. The t ratio that we have here, so this t ratio is simply, now what we have is we have the standard error calculated here, and here we have the sample mean minus the population mean divided by the standard error. So again, this here is just the t ratio. So the t ratio is t equals the mean from the sample minus the mean from the population divided by the standard error. And then last but not least, what we see here is a p-value of 0.13 and change. So again, I want the two-tailed test, so that's why we have a 2 in the function here. So E5 minus 1 is the sample size minus 1. That's the degrees of freedom. And this is just the absolute value of our t ratio. And in this case, it would need it because the t ratio is negative. So summarizing this information, if I go back to the whiteboard. So now what we have, we saw that the t ratio was, so for our problem, the t ratio was negative 1.636. The p-value for that t ratio, the p-value for our two-tailed test was 0.13 and change. This is very clearly greater than alpha. So our implication is that we fail to reject the null. If we fail to reject, then there's not sufficient sample evidence. Okay, so that would be our conclusion. And I believe that's a fair statement of reading it. So in other words, our average was not 105. Our average was not 105. The average of our sample was actually 100.55 or 101. All right, 101 does not equal 105, but if we account for the fact that there's random variations in the samples, random variation in what's actually being detected and how it would be detected, you're not always going to get exactly 105. And what we're seeing is that amount of being at 101, a little less, is not so extreme that it suggests that that we've actually violated, that anything nefarious is going on. It's not like they're cheating us. Now, if we go back, we can then also ask, well, what about that second part? So what changes with our second picture or the second scenario that's here? So now what about this part? What about where we test the claim that the detectors are under detecting? What would under detecting be? Okay, so if the claim is that the detectors are under detecting, in this context, the alternative is not that mu is not equal to 105, but we're specifically stating that mu, so in this context, we're saying that mu is strictly less than 105, less than 105, which means the alternative would be greater than or equal to 105. Now, do you see this now is a one-tailed test? So this now is a one-tailed test. So what we would need, now is this value. So the one-tailed value is 0.065. Let me draw the picture. Let me draw the picture for the one-tailed test on the whiteboard. So this is the picture for the two-tailed test. So what we're going to do is we'll go ahead and change this. So now it's, even if it's still 0.02, we're getting rid of this. And this is now our picture for the one-tailed test. And our p-value is no longer 0.13, it's 0.065. But we notice that it's still greater than alpha, so we still fail to reject the null. So in this case, our conclusion kind of just still comes out the same. So our conclusion is still the same, which is that I think that's the way we would restate the claim in this context. So let me just give you a kind of a real quick note with the template that I've provided you here. So with this template, this Excel template, what I want to emphasize is that, so the way this template is written here, if you just change this column B and put in the column data, if you have your data and you put it in column B, this template, if you have this typed in, will update automatically. The only other thing you would need to change is this value here. So these are all going to change based on what you have here, but you'll want to make sure that you've recorded your new value correctly based on what you're actually interested in for the problem you're focusing on. All right. Now, that said, if on the other hand, you've been provided the sample statistics, i.e. you don't have the actual data, but you have the mean, standard deviation, and sample size, you can actually just type those in here directly. So you can replace what we have here with the sample statistics, and you don't even need the actual data, and this will still run. So in that case, you need to replace all of the light orange content for it to update correctly.